Here we go. This is a continuation from the last lecture where we talked about periodic structures. The key things to come away with that were the lattice vectors, the idea of a reciprocal lattice and a direct lattice, that the reciprocal lattice vectors are grading vectors. And remember what a grading vector is. It's in the direction that the permittivity is changing, and it has a magnitude 2 pi divided by the period of the change in the permittivity. Then, I think it was in a lecture before that, we talked about phase matching at an interface where we had these index ellipsoids, we had a wave coming in and a wave coming out, and we tilted the wave until the phase matched up and we could figure out what direction it would refract. And that was called phase matching. So all this stuff is going to come together in this lecture, and this is actually a really important lecture because the stuff we're going to learn here is going to crop up in about every method we learn for the rest of the semester. So I'll review very quickly Fourier series. And I don't know if you knew this, but I know you know there's a one-dimensional Fourier series, but there's two-dimensional, three-dimensional, and you could keep going. There's no end to it. We'll stop at three-dimensional because we live in a three-dimensional world. Then we're actually going to look at diffraction of a wave through something that's periodic and put some additional math to this and come up with something that we call the plane wave spectrum. And this actually comes up a lot. And we'll generalize that to crossed gratings, which it's periodic in two directions now. And probably the most important thing is talk about power flow through these, because all the methods from here out, we're going to treat everything as if it's periodic. A wave goes in, it's going to split up into different directions. We're actually going to calculate how much power is in each one of those different directions, and then we got to add them all up. So that's how we're going to calculate transmitted reflected power. Here we go. Fourier series. So in this class, we're not interested in the sine cosine Fourier series, although there is some interesting things that can come out of that. Instead, we're going to generalize it a bit, and we're going to use the complex Fourier series, which hopefully you've all seen before. If not, we can take any function that's periodic and write it as a sum of a bunch of different complex exponentials. And we know complex exponentials are sines and cosines, right? And each one of these complex exponentials is weighted by some number, and we can calculate the number. So essentially, we decompose a periodic function into a series of sines and cosines. And if you add up all those sines and cosines, you get your original function back, right? So that's a Fourier series. We can do the same thing with things that are periodic in two dimensions, like checkerboards. And now we have a double summation, and it looks very similar. We can calculate the weights, A sub PQ, two-dimensional Fourier series. And the last one, we can be periodic in three dimensions, and we have a three-dimensional Fourier series. And we're actually going to use this one when we get to the technique called the plane wave expansion method. Although I don't think we're actually going to implement a 3D code in this class, so we'll go down to 2D, but it'll come up again there. So is everybody good on the Fourier series stuff? I wasn't going to go into too much depth there, but it's important that you know that there is two- and three-dimensional Fourier series.
The integration was second. Is that triple? Is it supposed to be triple?
Oh yeah, good point. Slide 6. Thank you. Thank you very much. That's the danger of copy-paste. Okay. On to the real stuff. We'll talk about diffraction from gratings. And you're going to see some slides that you've already seen. We have a wave passing through some kind of dielectric structure. Obviously, the wave slows down through this, and that part of the wavefront gets delayed. So we have this perturbation in the wavefront that resembles the shape of that object, is the point. So then here's the key thing we talked about last time. When a wave travels through something that's periodic, the field takes on the same periodicity as the structure that it's in. If it's passing through an array of hearts, that doesn't mean the field's going to look like hearts. It's just going to have the same spacing as the heart. So it only takes on the same symmetry, not the actual same look. Now, the different thing we're going to do with this today is we're going to show that when a waveform becomes periodic now, because it traveled through something periodic, we can decompose that into a Fourier series. And in fact, each term in that Fourier series is going to have the form of a plane wave traveling at a different angle. And so we're going to call that the plane wave spectrum, all these different discrete modes. And they have different discrete directions. It's not a smooth fan out. It's definite discrete directions. So, sorry, I'm starting over. We have something that's periodic, and anytime a wave is periodic, it's going to split into these multiple directions. So here I am showing a wave coming in. It hits a grating, and as soon as it does that, the amplitude of that becomes periodic. And as soon as that happens, it really is this plane wave spectrum that we'll get to, but it reflects in multiple directions and it transmits in multiple directions. And we're going to call these spatial harmonics. Now, the directions of these we can find very easily through this, what we call the grating equation. We have the refractive index on the top. We have this is another refractive index on the top. We have the sine of the angle of incidence. And then the sub m is the diffraction order, the 0, plus minus 1, plus minus 2. And so that'll be the angle of our mth diffracted mode. And so since we have any number of m, here's where the m comes in. And m is an integer, which goes from minus infinity to positive infinity, times wavelength over the period of the grating. So all these diffracted modes have different angles. Same equation now. The difference is now we're interested in a wave down here, so we put in the refractive index in the transmitted region. Everything else is the same. Just we changed and put in the different refractive index of whatever material we're in. So the thing is, we can calculate directions with this simple little analytical equation, but we can't answer how much power goes into each of those modes. All we can say is the direction that it goes. We have to go solve Maxwell's equations to figure out how much power goes into each of those. Does that make sense? Okay. And I'm not going to go through the derivation of the grating equation, but it's actually just the phase matching condition, and it's pretty easy to show that, but we won't get into that. Let me move this little block over so you can see the slide titles. So here is the effect of the period of the grating. On the left, we have a very, very fast grating relative to the wavelength. So it's really, really sub-wavelength grating. It's so sub-wavelength, it really can't even chop up the wave. So when a wave comes in, all it does is just go straight. It doesn't diffract at all. It doesn't split into these multiple modes. Well, if we stretch the period a little bit, at some point, we're going to start to see these diffracted modes appear. And they're going to appear first in this direction. And then they kind of come down as we stretch the period more and more. I have a movie of this that'll, I think, illustrate this. Here's just a summary of it. If we keep stretching it, now all of a sudden we're going to see diffracted modes being reflected. And if we keep stretching it, there's just more and more and more modes. But they're starting up here and walking down. And for very, very long period gratings, we get thousands of diffracted modes. If y'all remember that UTEP logo thing, that's a very long period grating, and you saw thousands of little tiny dots. If we tightened that up and had a much shorter period, you'd see many fewer dots, in fact. Now we're equipped to talk more rigorously about this plane wave spectrum. So we're convinced now we have a wave, it travels through something periodic, and in some way it takes on the same periodicity as the thing that it's in. So I'm just going to take this slice in the cross section and plot it. That is a periodic function, right? I can decompose that into a Fourier series. So here's the field. This is the thing that looks periodic. That's this. There is potentially this plane wave phase tilt term where the wave just coming at normal incidence, this ends up disappearing. So this is actually the thing that's periodic. So this is the thing that will expand into a Fourier series. So this is the complex Fourier series expansion of this periodic function A. Our weights that we before called A, we're going to call S. So S is going to be the amplitude of the nth order harmonic. S sub m will be the amplitude of the nth order harmonic. So x direction, left and right, y direction here is up and down. So this is still potentially a function of y. So we'll put in the y dependence there. Okay, so all I did was expand this into a Fourier series. Right? Okay. And here's how we would calculate the amplitude. So we had a periodic function. We expanded into a Fourier series. And now what we're going to do is just rearrange some terms. We're going to bring this e to the j beta r into and combine these two exponentials. When we do that, this is only an x component. This has both an x and a y component. So we pull out the x component of it, put in this complex exponential, and then the remaining y component of e to j beta y. So everybody follow that? So all we did was bring this complex exponential into this one. Now I'm going to define a term. I'm going to call it kx sub m. And it's just what's in here. Now I have e to the jkx m. So kx is going to be different for each of these harmonics. And then we still have our beta y. Well, we can now bring this into a single exponential that looks like a j k dot r, like over here. And this is the sum of a bunch of plane waves. So this is exactly the same form as a bunch of plane waves at different angles. So it's not even an analogy, it is exactly that. Any kind of periodic electric field, we can always decompose into a bunch of plane waves at different angles. And Fourier theory says that that has to be possible. So this isn't an analogy, that is reality. So that's why when a laser pointer goes through something periodic, and it chops it up in all these different plane waves, then if you go very far away, you can let those plane waves separate, and you'll see the separate dots. So in the UTEP logo, that's why you see the separate dots. Now up close to the thing, you wouldn't see the UTEP logo because all the plane waves are still overlapping. You got to sort of let them separate a little bit. Okay, everybody good? So here is the plane wave spectrum all in one picture. We got a periodic field, and we wrote it in this form, and plane wave spectrum, periodic field. And it's very useful to speak in terms of the plane wave spectrum. There's a lot of meaning that you'll get out of that. Later on, I'll step you through an example where it was actually me competing with an entire company, and we were modeling these really crazy photonic crystals, and they measured their transmittance on something called a Fourier transform infrared spectrometer, and they couldn't match the experimental results. They had no idea what was happening. And what it turned out is the thing that they were measuring diffracted, but this FTIR instrument only was able to record the zero order mode, the thing that went straight through. So in their model, they were accounting for energy everywhere. In my model, I ignored that because that's what the spectrometer was doing, was ignoring that, and it was a virtual overlay. So that's where the art of modeling comes in. But if my codes didn't have the ability to decompose fields into the plane wave spectrum, I wouldn't have had the ability to do that. And I suspect that's maybe one of the reasons that they didn't realize that, because they weren't decomposing their field into these spatial harmonics. So there is definitely utility to it. So periodic fields can also be represented as a bunch of plane waves at different angles. But we don't know the amplitudes of them. We'll know the directions from the Grating equation, but we won't know the amplitudes. So we have a wave coming in, we have a grating of some sort, something that forces the field to become periodic. Well, now we know the x component of the wave vector through this equation. The grating essentially chops up the wavefront, and we have this really an infinite array of x components, because there's an infinite array of these plane waves, in fact. So we have an infinite number of them, but we still have to determine the longitudinal component of these wave vectors. And we go back to the dispersion relation for that. And if we solve for the longitudinal component, in this case I'm using y, we get the square root of the magnitude of the k vector minus this kx term squared. Now here we have the square root of a difference. This could potentially become imaginary, right? If the argument's negative, it's imaginary. And so we'll have a wave that always has a real wave vector in the transverse direction, so it's always going to push energy to the sides, but there's this chance now that it'll decay in the longitudinal direction if the argument is negative and the ky component becomes imaginary. Does that make sense? So here's the full story. We have an incoming wave that hits something periodic. Because it's periodic, we get an infinite number of these kx vectors. And so I put kx and the 0 there, or the +1, +2, that's the diffraction order number. And as that integer m gets bigger, so does the kx component. So we phase match that into the second material. And what we'll find out is at some point these kx vectors are too large. It's describing a wave that varies too rapidly to match into this material. So at some point, these become cut off. They're not propagating waves anymore. They're cut off. They're confined to the surface. But these lower order ones really are propagating waves. It's just that their k vector on these higher order modes becomes so large they can't phase match into this second material. They become cut off. Everybody okay with that? So even though we call this the plane wave spectrum, usually only the lowest few order modes are plane waves. Everything else is cut off and evanescent. So it'd probably be better to call it the evanescent wave spectrum, but we don't. We call it the plane wave spectrum. But most of these are evanescent and cut off. There's an infinite number of these kx vectors. They get bigger and bigger and bigger. The bigger they are, it's describing a very short period thing which cannot phase match into this material. So it's cut off. So how's everybody with that? Onward then. So here's the conclusions that I'd like you to come away with the plane wave spectrum. Fields in periodic materials take on the same periodicity as the thing that it's in. We can expand a periodic function into a Fourier series. Each term of the Fourier series is now a discrete thing, and it becomes a plane wave at a discrete angle. We have an infinite number of them, but they get bigger and bigger and bigger, the x components. At some point they can't phase match, and those higher order ones become evanescent. And it's usually only the first 3 or 4 that are actually plane waves. And so that's the story. How is everybody? I don't see any smiles about this. This is good stuff. So that is just from a one-dimensional grading. I want to generalize this to what we call crossed gratings. So we just talked about what in the literature they sometimes call a 1D grading because it has periodicity only in one dimension. Sometimes it's called a ruled grading. And this actually requires a two-dimensional simulation, a two-dimensional model to be able to calculate everything about that. If we move to what's called a 2D grading, because it's periodic in 2 dimensions now, we call it a cross grading, and to model this requires a 3D simulation. So there's the potential for confusion in words. A 1D grading requires a 2D model. 2D grading requires a 3D model. I try to avoid those terms because it's confusing. I just use ruled grading, crossed grading to avoid the confusion. But there's the words, and if you read the literature, you'll see that. So now, rather than having diffraction really confined to a plane, it diffracts in all directions. So if we have an incoming wave, it hits something periodic, whatever that might be, it will transmit and reflect into a whole series of plane waves, all at different angles. But the same thing holds. The higher order ones will become evanescent. My artistic abilities start fading me there, and I can't draw them. So I draw them as plane waves, but in fact most of them are evanescent. Those higher order ones, the ones that are out from the middle. The other thing you want to keep in mind when you see pictures like this is that the waves themselves are not at physically different locations. They're plane waves and they're of infinite extent. So in fact they're all overlapping. It just becomes, you can't see it at that point. So I physically separate them so you can see all the plane waves at different angles. And now that we have a cross grading, we not only have this expansion in the x component of the wave vector, we have the expansion in the y component. So we'll have that transverse plane be the xy plane, and then the longitudinal direction be z now. So in order to calculate the wave vectors associated with all these, here's how I like to do it. I calculate the diffraction indices. So big M will be an array. Let's say this big NX is 11. M is going to go from -5 to +5. And we'll be counting for 11 harmonics in the x direction then. Up here I have, see, 1, 2, 3, 4, 5. So for this expansion I'm showing up here, big NX would be 5, and this big M would go -2, -1, 0, 1, 2. It passes through 0. And N's the same thing, but it's for the y direction now. Then we can calculate the Kx and Ky. These are now going to be 1D arrays. So Kx is only going to go along one axis. The Ky will only go along one axis. But we see we actually have a mesh grid of these things, right? So that's the last step. We'll mesh grid them. And now we actually have Kx and Ky being 2D arrays describing the x and y wave vector components of all those harmonics. And we'll be using this when we get to rigorous coupled wave analysis. That's where we do the cross grading diffraction. Okay, everybody good? So here's what these look like in my mind anyway. When I'm thinking about the Kx mesh grid, this is really what that array would look like. We're talking about the wave vector components at every point, and since it's only the x component, they're always pointing in the same direction. Then the Ky components, it would look like this. And really, when we put them together, we're looking at transverse wave vectors that look like this. So these are all pointing within the plane in all different directions, kind of fanning out from the middle, the zero order harmonic. So that's just how in my head, I envision those mesh grid arrays. It's just the transverse wave vector component. It's just the wave vector along the parallel to the surface. So how do we calculate the longitudinal component? That comes from the dispersion relation again. Because the magnitude of K is fixed, we know two of its components, we can calculate the third. So we go to the dispersion relation to do that. And here's our two equations for calculating the longitudinal components. Now the reflection and transmission regions above and below your device can be in different materials, so we have to calculate them separately. And for those of you that got that far in the transfer matrix method, you did that. You had to calculate the Z component on the top and the bottom differently. So we calculate the transverse components on the previous slides. If we looked at the Z components in one of them, that's probably the best way to envision it. The center few are actually real, and those are the propagating waves. The rest are cut off. We still need to have them there and account for them, because they still say a lot about how the device is going to behave, but they're cut off. They don't actually propagate as waves. Everybody good? So here's a better visualization of it. The upper left, we have the transverse components. On the right, we have what the Z component of the reflected wave vectors look like. Now, if we were to tie all this together, this would be a way to visualize the reflected modes. The center few are real propagating waves. The rest of these higher order diffracted modes are cut off. On the transmitted side, we're probably going into something with a higher refractive index, so a lot more modes are supported, a lot more diffracted modes, but at some point the rest are also cut off. That's the best way I can visualize these arrays for you guys. Any questions on that? Now let's talk about power flow. So power in electromagnetics is described by the Poynting vector, right? E cross H tells you the direction that power is flowing, and that's a cross product. E and H are vector quantities. So that's the time domain equation here. That's the instantaneous power flow. Well, a lot of times we're modeling this in the frequency domain. We're really interested in more of the average power flow, the RMS power flow, in which case it's E cross H, but we take the complex conjugate of the H, so we end up with a real number overall. 1/2 the real part of E cross the complex conjugate of H. So hopefully you saw that in electromagnetics. If not, you're seeing it now. So rather than keep writing R and omega, we'll just write it real compactly like this. But that is in the frequency domain, the average sort of RMS power flow. Is that familiar to most of you guys? Okay. You probably saw something similar in circuit theory. You had a V times I complex conjugate for calculating power. When we're calculating power flow, it's going to be outside the device. The materials are going to be linear, homogeneous, isotropic. E and H will be at 90 degrees with respect to each other, and also 90 degrees with respect to the Poynting vector. So they're going to all be orthogonal to each other, and we're going to use that. Since everything's orthogonal, the Poynting vector and the wave vector have to be in the same direction. They don't have the same magnitude because they're talking about different things, but they're in the same direction. Since they're in the same direction, then if I take the Poynting vector, divide by its magnitude, I have a unit vector in the direction the wave is moving. And I could do the same thing with K. I could take K, divide by its magnitude, I have another unit vector, and so these two sides have to be equal. Right? So now what I can do is figure out what this cross product is. Since I know they're at 90 degrees with respect to each other, I know the magnitude of the cross product is going to be the product of their magnitude separately. The magnitude of E times the magnitude of H. That will be the magnitude of the cross product because they're at 90 degrees with respect to each other. I also know the direction of the cross product. It's in the direction of K, or the Poynting vector, or wave vector. So this cross product then has a magnitude and a direction. And that's how I go from here to here. So I've eliminated the actual cross product in there, and I could do that because E and H are perpendicular. Everybody's good, okay. Now we're going to eliminate one of the variables. And we could choose either or. In this case, I'm going to eliminate the magnetic field. But if we are talking about a plane wave, the magnitude of E and the magnitude of H are related through the material impedance. So E over H is this material impedance. Kind of think of that like Ohm's law, where E is sort of voltage, H is sort of current. Voltage over current gives you impedance. So we can use this relation. We can solve for H and then go in and replace H with that expression. If we solve this for H, it's E over eta. So in the end, we get the direction, and now our magnitude is E squared over eta, the impedance. So we just eliminated H. That's all we did there. Everybody good? So the Poynting vector can be at an angle. We're really only interested in power that's leaving or entering our device. So we only want to listen to the Z component of it. We only want to listen to power that's moving up and down. If it's moving to the side, it's not leaving our device. So in terms of calculating transmission and reflection, we ignore that. We only listen to power going straight up and down. So we're only interested in the Z component of the Poynting vector. So This is the pointing vector we had from the last slide. If we only listen to the z component, it's no longer a vector, and we have this equation. Everybody good with that?
No longer a vector.
Because it is a vector, but we're only interested in the z component. So we're only proceeding with the z component, so we don't have to treat it as a vector anymore. Make no mistake, it is still a vector for sure. Everybody good? So we had a field and something periodic. The field itself was periodic, and we decomposed it into a Fourier series. And we set the amplitude of that wave to be capital S sub m, where m is the order of the diffraction, right? So if this is the amplitude, we could just put that in place of the E, because it's still an amplitude term. And now we're setting ourselves up to calculate the power in the mth order harmonic. And that's why we have the amplitude of the mth order harmonic there. So you see what I did? So now there's going to be, there's a pointing vector associated with each of those harmonics. That's the z component of each of those harmonics. So the power flow of the incident wave, it has some amplitude, and it's coming in with some k-inch wave vector. So that'll be the power coming in from the incident wave. And we're going to do a similar equation for the transmitted reflected waves. First, we're going to define something called diffraction efficiency. And we pick a particular diffracted mode. The fraction of power that goes from the applied wave to that diffracted mode is called the diffraction efficiency. So if your diffraction efficiency is 50%, that means half the power from the applied wave ended up in whatever diffracted mode you're talking about. In some ways, I don't like calling it efficiency because it always seems like, oh, we want to be really efficient. We always want that high. Not necessarily. Sometimes we want it low. For example, to make that UTEP logo, where we had the UTEP letters, we want a high diffraction efficiency, and where we want black, we want a low diffraction efficiency. So even though we call it efficiency, don't judge on whether it's big or small. It's just how much power goes from the applied wave into that. So we can define diffraction efficiency as the power in the nth spatial harmonic divided by the power in the applied wave. Now, there's only so much power going in. The power gets divided up into all the reflected modes, and it gets divided up in all the transmitted modes. It makes sense. If you added up all of these, you should get all of your energy back, assuming you don't have any loss or gain built into your model. So this is a great check to make sure everything's right with your model. You add up all the reflected powers, all the transmitted powers, and you should get 100% back. Okay. So this is the power coming in the applied wave. This is power leaving in the reflected harmonics, so m's an integer. And here's power leaving in the transmitted harmonics. And that's the m's the order of the diffracted mode. We defined our diffraction efficiency as the ratio, so let's do that. Let's look at the diffraction efficiencies of the reflected modes. We have the pointing vector for the nth order mode divided by the applied wave. And we turn the crank on the algebra, we end up with this equation, which you'll recognize from a previous lecture of how we were calculating reflectance in the transfer matrix method. And I said we were deferring the derivation of that equation until now. Let's do it for the transmitted harmonics. Power in the transmitted mode over the applied power, and we end up here. Now, when you divide these things, there's actually a bit of algebra leading up to this, and I believe that's in a homework assignment. Here's some tricks. The impedance in the incident region is the same as the impedance in what we call the reflection region. That's both sitting on top of the device. And remember that impedance is the square root of mu over epsilon. Remember properties like that. And so when you take the ratios, you can use all this information and eventually end up with the equations down below. So any questions there? Do those equations seem weird? All right, onward then. So what we did was derive those diffraction efficiencies equations in terms of the electric fields. We could have done it the other way and derive it in terms of the magnetic fields, and we end up with the red equations at the bottom. The blue equations up top are what we just derived. If we went back to that one slide where we had E over H equals impedance, and we use that to eliminate H, we could have also used that to eliminate E and then proceed with H. And those are the diffraction efficiency equations we would have ended up with. Now sometimes when you model a device, you'll calculate the electric fields like you did for transfer matrix methods. So you'll use the blue equations here up top. Other times you'll be solving it in terms of the magnetic fields, and then you'd use the red equations down below. And the only difference is which one you eliminated at the beginning of the derivation. Everybody good? You guys feel like you could do that derivation? It's outlined here if you follow that. So.